All right. If you have further questions, of course, you may continue asking, but right now we can start with our new discussion. The new discussion, before okay, so the name of the course is Signals and Systems, hence but previously, the last time we were talking about a concept called convolution, and convolution is strongly related with systems. So I want to start by giving some examples of systems. We will have two types of systems, clearly. One of them is continuous time system acting on continuous time signals like this. And the other one is, a discrete time system acting upon discrete time signals. The input is discrete, the output is also discrete. The signals that are necessary for defining a system are the output signals, because sometimes the systems may have their own initial conditions, which can be considered as an input actually. So that is also some sort of an input perturbation of the system. And the output is the observation. Without observing the system, we have nothing to say. Well, we have a typical system example, and this also briefly explains why we are having the Signals and Systems course in electrical and electronics engineering. And you will understand that a system could actually be, could be a circuit like this. This may be a little bit too complicated, but what makes it a system is the input part, which is usually drawn at the left-hand side, and the output part drawn at the right-hand side. The input is therefore here, x of t, which can be a voltage waveform. It can be a unit step function, which is a very classical input that we are familiar with from circuit theory and electronics. And the output is maybe the voltage across this capacitor. And we can call it y of t, which is also in terms of the volts changing in time. Like this. So this is a system. But don't fix your minds to this kind of a system only, because systems are very general things where you must have an observation. For instance, the algorithm that runs through a computer could also be considered as a system. The inputs may be, for example, the stock values or the financial values of the next value of the stock market. So it's a predictor system. In the next day, for example, or the next hour, it is a discrete system, and it is a system. It's a computer algorithm. So as you see, it may be an algorithm, and the data could be just anything, finance data, or the dynamics of a space shuttle, or it could be the genome of a living species, including human genomic data. Okay. Nowadays, of course, discrete signals or data is more valuable. It can be multiple dimensional signals, like an image, two-dimensional. It's a three-value, two-dimensional thing. That's what we call a color image. Why is it three-valued? Because at every coordinate, we have red, green, and blue colors. So three different values occur. It's not a single valued function that we are familiar with in terms of drawing. Or a video, for example, is a three-dimensional signal. And it's a hybrid three-dimensional signal for television, because horizontally it's continuous for TV, analog TV I'm talking about. But vertically it's discrete because there are lines. And temporally, time-wise, it's also discrete because there are so many frames per second that are coming. They are multiple dimensional signals. It's not 1D signal. Of course, in this course, we are dealing with mostly one-dimensional signals, but for your projects, you may proceed to, let's say, image processing. That's something nice. So, for instance, an edge detector is a system where the input is an image, the output is also another image exhibiting only the edge points of a certain image, depending on the change or variation of the intensity alongside the image. And of course, we have to interconnect. We may interconnect systems. They may be, I will continue from the top, they may be a system cascaded to another system, or here we may have another system which also acts upon the same original input, and then the output may be combined like this, right? So how can we, if we can analyze each of these individual boxes, particularly in linear systems, I will explain what a linear system is very soon, then we can make sense of such combinations as well. A very popular interconnection methodology that is particularly used for control systems is so-called feedback, like this. So there is an input, and then there is an output, and that output is also processed with another system, and that process signal is added to the input as a feedback. Such things are called feedback systems. Once we develop the tools to analyze systems, you will be able to formulate and come up with the overall input-output relation from this input to this output by saying that the dashed box, the larger thing, is your system, and how does it behave if the top and the bottom blocks are already given to you. Now, I will do a few examples, and the first example again will be a circuit example. Okay, somebody are still coming, so I'm admitting them. The example that I will show you is a circuit example, but a simpler one. It's a simple RLC circuit, not as complicated as the one that I gave above. It is consisting of a single resistor and a single inductor and a single capacitor. That's an RLC circuit in the simplest sense, where the input is x of t, which is the voltage variation in time. Let's say this is plus and this is the minus pole. And again, the output is the voltage through the capacitor obtained as y of t, where this is plus and this is minus. This is a simple RLC circuit. Now, be careful about this. I'm going to write the formula or the solution to this kind of an RLC system from the perspective of a dynamic system, that is a differential equation. It will be an ordinary differential equation because we don't have a time-varying resistor or time-varying or voltage-dependent inductor or a capacitor. These are linear circuit elements, and if you have linear circuit elements, you come up with a linear system. That's the name, okay, linear circuits and linear systems. And for linear systems, we will come up with an ordinary differential equation with constant coefficients. So what is that differential equation that we will come up with? From circuitry, you may remember that we write the current loop, and I'm going to call it I of t, because it's also changing in time, depending on the changing in time of the input voltage of x of t. So what is the voltage equation? Let's say that this is R, this is L, and this is C, okay, as the values. Let's leave them parametric. R times I of t is the voltage across the resistor, okay? And L times the time derivative of the current I of t is the voltage across the inductor, okay, and plus the output y of t, which is the voltage that we are measuring through the capacitor. We call it the output. You could say minus x of t is equal to 0, which makes a complete voltage loop. So, and the second differential equation is the connection of the current I of t to the capacitance value by the derivative of the voltage through the capacitor. So the time derivative of that voltage. What is that voltage? We gave a name to it. It's y of t. So this is the current. And the current is the same throughout all the components. It's just cascaded components. So we have these two equations. Let's now combine them. Let's substitute I of t is equal to c times the derivative of y of t into the first differential equation. And then we will have like r times c times, let me say y prime of t, the first derivative, because it is I of t, r times I of t. I'm writing this one, plus L times the derivative of I of t, which will give me c times y double prime of t, the second derivative of y of t, because I of t is the derivative of y of t. Derivative of I of t is the second derivative of y of t. And y of t, I will also keep it like this, is equal to x of t, okay? This is a second order differential equation. It may be good to order this differential equation a little bit so that the second derivative comes first. LC y double prime of t plus RC y prime of t plus y of t is equal to the inputs. This is the second order ordinary differential equation. This equation in the box or below it, that differential equation, is the system. Because how else can we define or describe a system? The only way to describe a system that we are aware of for the time being is this input-output differential equation in the form of a derivative. In the form of derivatives, there may be derivatives of the output at the left-hand side of the equation, and at the right-hand side of the equation, we may have the input and the derivatives of the input too. That's also possible. But second order is an interesting order for differential equations, because most of the linear systems, eventually, in physics, they come up with second order differential equations. Look at another example. The next example is a mechanical system. And we have this wall, let's say, and we have a mass here. The mass of this mass is m, okay? And there is a spring here. It's not a resistor, okay? This is mechanical. It's a spring. And there is a damper. The damper is notated like this. That is also connected to the mass. And the mass is connected to a user which applies a force to the right-hand side. And this is the horizontal axis that we observe. So the output is the position of this mass. This is how I define my mechanical system, the position of this mass. Initially, it was here at 0 point, and the horizontal axis is, let's say, in meters or centimeters, whatever. You have to, of course, have compatible units for measuring. So this is the output. What is the input? The input is the force that we apply. We are pulling this mass. So how can we describe the motion, y position, that changes in time according to the change of the force x of t in time? So what's the relation between x of t and y of t? So this is spring, and it is a spring constant, which is notated by K in physics. You may remember those from high school physics. You may be. This is that is something that we haven't seen in high school, but maybe in college school you may have seen it. This is the damping, and the constant for damping is notated by D. Okay, damping constant D. Now the force balance is the thing that we have to write. The loop equation or the circuit equation, going to write the force balance. First of all, there is one thing that is the output, and that is the net force. Does any of you know the definition of force? What is force with respect to mass? Mass times what is the force? Anybody from there?
Acceleration.
Acceleration, excellent. Yeah, someone wrote and someone also told. Mass times acceleration is the force. So let's write it. Mass times, what is the acceleration? I'm saying that it's this. It's the second derivative of the position. The first derivative of the position will give you velocity, and the second derivative of the position will give you acceleration. So it is essentially m times y double prime of t. That is the acceleration of this mass, this moving mass. It's the net force. So what is that force balance? There are two things that are acting in an opposed way. One of them is, let's say the positive way is to the right-hand side, to the position of x of t. So we have x of t acting positively, minus all the others pulling backwards. For instance, minus spring. The spring pulls back with respect to how much the spring is stretched. So it depends on y of t. If y of t is more, then it pulls back more with a spring constant multiplied by a spring constant. It's simple. It's k times y of t. That is the spring pulling the mass back. And the other one is the damper. The damper resists to the motion and applies a force for faster speed. So if you are moving abruptly with high speed, then it pulls back. But if you are moving slowly, it doesn't pull back a lot. It's a damper rail. You may notice that I don't know the English name for this thing, that the injector, okay? The injector. If you push the injector very fast, it resists, but if you push it slowly, you can easily make an injection, medical injection. So it's something like that. The damper is actually something like that injector mechanism. And that is therefore constant times the velocity, which is y prime of t. So that's it. Let's now combine all the terms related to y of t at the left-hand side, and it will give me m times y double prime of t plus d times y prime of t plus k times y of t is equal to x of t. Look at that. And look at the previous one. As you see, they are almost the same. They correspond to something quite different in terms of physical nature. One of them is electrical circuitry. The other one is just mechanical motion. But the physical essence of it are more or less the same. Second order differential equations is what we get. There may be, of course, initial conditions. You may be interested in those things. But Nonetheless, very different class of signals or systems can be described using a similar characteristic. That similar characteristic is differential equation, particularly, there are some people in the waiting room still, particularly in second order differential equations. Right. Now let me give you a discrete time example, which is an edge detector. The edge detector that we are interested in discrete time and in images, in profiles, is usually looking at the second derivative. Why are we looking at second derivative? Because we want to take a look at, or we want to exhibit some large number for a ramp kind of a change in the intensity, in the darkness or lightness profile, like this. So let's cut the image horizontally and we look at a one-dimensional profile, and let's say that it looks like this. It is zeros here, and starting from 1 it becomes 1, and then 2, and then 3, and then 4, etc. It goes on like this. So as you see, there is a ramp, and we want to detect the starting point of this ramp, because that is where the edge is. We want to detect that point. You may think of some simpler ad hoc techniques for edge detection. You may say, let us apply a threshold, and whenever it is non-zero, let's call an edge. But technically, in practical image processing, it doesn't work that way. You must look at either the derivative or the second derivative. For this, it's best to look at the second derivative for another class of edges, which are like unit steps. If you want to detect this edge, for example, it's a simpler edge, then it is best to take a look at the first derivative. But of course, these are discrete time. So what do we mean by derivative? What we mean is difference. So in discrete time, a derivative is transformed into a difference. What is the difference? For example, instead of d by dt of x of t, we take a look at, this is the first derivative. So instead of this, we take a look at the first difference, which is x of n minus x of n minus 1. It is an approximation of the derivative. If you remember the finite approximation of derivatives from calculus, we subtract two consecutive values and we divide by the time difference. So x of t plus tau minus x of t over tau, the time difference. But the time difference here is 1. Therefore, we don't need to divide anything to that. That's why I'm safely saying x of n minus x of n minus 1 as the first difference. How about the second difference? That is the second derivative, excuse me, that is reflected as the second difference. So it is like x of n, x of n plus 1 minus x of n, which is one difference, minus x of n minus x of n minus 1. So as you see, we have a first difference here, another first difference here, and the difference between these first differences in time will give me the second difference, which is like the second derivative, but there is a shorter way of writing this. It is x of n plus 1 minus 2x of n plus x of n minus 1, like this. So basically, this is the second difference. Now, as a kind of exercise or a homework, you may think, apply this second difference to this input. And one by one, write down the terms. First of all, for everything that is 0 at the left-hand side, x of n plus 1 and x of n minus 1 will be the same. Let's look at the left-hand side. So the x of n plus 1 and x of n minus 1 will be the same. And x of n will also be the same. They will all be zeros, by the way. So they will all be zeros. So 0 minus 2, 0 plus 0 will give you 0. For the very right-hand side, ramp positions. For the ramp position, there is x of n plus 1 and there's x of n minus 1. One of them is large, the other one is small. X of n plus 1 will be large, x of n minus 1 will be smaller than that. And x of n will have a value right in between. So I'm adding the larger one and the smaller one, and I'm subtracting twice the middle value. What will I get? 0. Because this plus this is exactly the same as the middle value in twice. If it is a line increase, of course, a linear increase. What I'm saying is this plus this is twice the value here. Okay, so if I subtract that twice value, again, at the right-hand side, everything's gonna be 0. So the right-hand side will give you 0. The left-hand side will give you 0, but something in between, during the transition from zeros to the ramp, something happens. So please try to find what those values are. And those values will be, of course, non-zero. And whenever that is a non-zero, you can detect it as the starting point of an edge. So you detect an edge like that. So a very rich class of systems can be achieved, you may think of, and you may imagine projects about those things. It may be discrete, it may be continuous, it may be regarding voltages or mechanical systems, or just data like the genomic sequences or images, biomedical signals that are acquired, etc. It may be multiple dimensional or one-dimensional. Just everything is possible over there. What time do we have? 14:39. Let me proceed up to a quarter to 3 o'clock, and then I will stop and give a break of 15 minutes. At 3 o'clock, we will start again. But before that, I want to continue a little bit further, because I want to very quickly, now that we have motivated what systems are, we have to talk about the system properties. Because these properties are the things that help us to analyze, to mathematically attack the problem. If you cannot detect some certain properties of a system, if you can say that we don't know the system, it's a black box, it's very difficult to make sense of that kind of a system. We have to first check whether the properties that I'm listing are available in our system, whether it is it obeys these properties. And the first property that we will look at, we will start from easier ones, and they are going to be easier to check, and we will come up with more important properties later. They are not more difficult, but they will be more important. This one is an unimportant one, that is memory. Does the system have memory? Well, the answer to this is, unless you come up with something very, very simple, the answer is yes, it is with memory. It's very difficult not to have a system with memory. For instance, let me go up a little bit. This circuit, or these circuits, as you see, there are capacitors inside. And the first thing that you have seen in circuit theory or in electronics is that a capacitor is an accumulator, and it has memory. It is accumulating all the previous, integrating all the previous data. So if something from the past, and interestingly, it may be from the future as well, is available to you, then it means the system has memory. It requires a collection of information from the past or from the future. Only when a system output is related with the input instant and nothing else, then the system can be called memoryless. Okay, but we usually don't have such memoryless systems. A simple memoryless system, memoryless systems are examples. Y of n is equal to absolute value of x of n, for example. If you're taking the absolute value of the input, then of course it does not depend on the past inputs or any other value, but only at x of n. A rectifier, for example, this is also valid for continuous time, of course. A rectifier is such a thing. Or if you are taking the square of an input, then of course it's again memoryless because you are only taking the instantaneous value and you're taking the square of it. I'm particularly a little bit curious about this, and you must take this notation carefully. X square of t means this absolute value is not necessary. It means x of t squared. Okay, that's what it means. It's taking the square of the magnitude. Notation-wise, it may look awkward because I'm squaring only x, not x of t or anything, but that's how we write it. When I say x square of t, it means x of t altogether squared. Okay? So these are typical memoryless examples, but or another example, of course, these are examples. Another example may be y of t is equal to cosine of x of t. This is also memoryless because it only depends on the value of x of t at time t. But all other systems will be with memory. And a typical example is y of n is equal to k from minus infinity up to n x of k. This, you may, or in continuous time, let me also write it, the continuous version of it. Y of t is equal to integral from minus infinity to t x of tau d tau. These are accumulators. They accumulate all the values from minus infinity up to the time instant. Everything is added. And accumulators are also known as integrators. In continuous time, of course, it's integration, but in discrete time, they also sometimes call it an integrator. It's integrating the input and coming up with a value. That's called note. Accumulators are inverses of derivatives or differences. So we had a difference operator, if you may remember. What was the difference operator? First difference operator. It was y of n is equal to x of n minus x of n minus, x of n minus 1. This is a difference. And then accumulator is y of n is equal to k from minus infinity to n x of k. I'm claiming that these two systems are inverses of one another. If you pass an input from an accumulator and then pass that output this time from a first difference, you come up with the first input signal, the starting signal. Or you may interchange their places as well. If you first difference signal and then apply it to an accumulator, you come up with the original input signal. These two are inverse systems. And by the way, the second property after the break will be invertibility. So Memory is one property of a system. Is it with memory or is it memoryless? That is one thing. And the second property will be, is it invertible or not? And we don't really have the detailed answer to that. We don't have the knowledge to do it right now. We can just by inspection, if you can find the inverse, it means it is invertible. But if you cannot find the inverse, it means it doesn't mean it's not invertible. Maybe you couldn't find it. But of course, as time evolves, we will come up with methodologies to find the inverse systems. There are ways to come up with the inverse systems, but we don't know them yet, and we will learn these things later. So the second thing, invertibility, is a loose property for you for the time being, because if you can find the inverse, it is invertible. You will have to say, for example, an amplifier, y of t is equal to 2 times x of t is clearly invertible, because you can say that z of t is equal to 1 over 2 times y of t. If y of t is the input, z of t is the output. That will give you x of t. So I could invert, multiply by 2, inverse is multiply by 1 over 2. Or if it is sine of x of t, what is the inverse system? It is arc sine, right? Or if it's the cosine of the x of t, like this here, then cosine inverse or arc cosine will be the inverse system. Right? I'm not going to go into the details of this one because we don't have the tools. We don't know the tools yet. But the inverse of this difference and accumulator and the derivative and the integrator, which is this one, together with its inverse, which is d by dt x of t. These two are also inverses of one another. You should keep this much in your minds at least. You know that accumulators and differences or derivatives are inverses of one another. All right, we are already doing a lot of minutes. So are difference operators memoryless? Yeah, there's a question. That's a good question, actually. It looks like memoryless, but actually in the discrete sense, if you think of it, they are with memory, because it is x of n minus x of n minus 1. So it requires x of n minus 1. It requires one memory, not infinite memory, but it requires one memory. And in continuous time, no matter how small that difference may be, it uses the past values in the history. So they are with memory. They are not memoryless. Yeah, it uses past values to operate at continuous time as well. That is true. No matter how near a past value it is a past value. But those are ambiguous questions, okay? Because you may interpret them to be so narrow. So if some student says d by dt of x of t is a memoryless operation, if he claims, and because of that he loses or she loses 10 points, I would not want to do that. Okay, they are ambiguous questions. They are not memoryless, they are with memory. Okay, that is the correct answer technically, but I would like to ask more open and obvious questions to you, not ambiguous questions. Both of them are correct. If you interpret it in this way, you answer it like this. Interpret it in another way, you answer it like that. Those are dangerous questions, and I don't like asking such questions. I want to ask you in exams. I would like to ask you more clear and obviously memoryless or obviously with memory questions, because I want you to know the concept. I don't want to punish you for just not thinking something that is not very critical. I don't want to do it that way. So now I will stop the recording.